Welcome back, everybody, and welcome Roksolana Diachuk to Pink Floyd stage. Here's what we know. Roksolana works as a big data engineer at Captify. She's passionate about big data, Scala, and Kubernetes, and she always loves to learn something new. Roksolana is one of the women who Code Kiev leads, so she enjoys organizing events as well as speaking at them. Her hobbies are building technical topics around fairy tales and discovering new cities by traveling. Whew, wish we can continue that soon. And Roxana will talk why big data is not data science. So here's a word to you, Roxalana.
Yeah, thank you. Hello, everyone. Today we are going to talk about big data and how it's different from data science. So I'm Roksolana, and as it was said, I work as big data developer at Captify. And Captify is a British product company with a product in the sphere of advertising. And actually, Captify is the largest independent holder of user searches outside of Google. Also, I'm Women Who Code Kiev data engineering lead. I'm speaking and traveling and a huge fan of big data and functional programming. So what is big data? Many people think that big data is defined in terms of its size. Like there is some kind of limit by which we can say that there is like normal data, maybe small data, and then there is big data. So for instance, gigabytes would be kind of maybe medium size or even big data. So terabytes might be like even larger. So definitely big data, and maybe petabytes, which means even larger, is definitely big data. But it's not completely true. In reality, there are multiple characteristics or aspects that describe big data, and this theory of these characteristics is named 5Vs, basically because all of these characteristics start with V in English. So the first of those is volume. Yeah, so again, we are talking about size of the data, but as we can see, it's only one of the multiple aspects that describe big data. And in reality, we don't have some kind of limit or definition to the big data. So we would say for sure that after this limit goes big data. Before that, it's not big data. In reality, we kind of have this imaginary limit by which we can say that usually in order to process big data, we need more resources. And by more resources, I mean distributed systems like multiple servers and so on. So you wouldn't be able to process large volumes of data on your local machine. And that's kind of an imaginary boundary, basically because we have such a huge variety of machines these days. So it's still kind of a speculative question in terms of volume size. Another aspect is velocity, and there is a notion of batch data and streaming data when we were talking about big data. Batch data means that we process data in such a way that the records are kind of combined in batches, not one by one, but in batches, like multiple records. And we can allow some kind of delay that we can process this data, for instance, with 3 hours, 4 hours delay. We mostly care about the final result. For instance, some monthly data, yearly data, and so on. And there is a streaming data. Streaming data has different nature. Usually it implies that we process each record one by one. It's extremely fast, and it's great when it's possible to kind of perform nearly real-time processing, which is quite a hard task. But it's totally two different types of data, but they can be combined into kind of in one project that can be used together. Another aspect of big data is variety. And by variety, I mean differences of formats. So it can be like structured data, like relational databases. It can be CSV files, JSON, even text files and images. And usually types like protobuf, Parquet, Avro are called big data types because they are like commonly used in the big data field. But it still doesn't eliminate other kind of formats. So we can see that various formats obviously means that we should use multiple instruments for that. Another aspect is veracity. And veracity in this context means connectedness of data. So some entities, for instance, in database may be so much connected or that their connection is more valuable than the actual information stored in these entities that we should kind of pay more attention to processing these connections, for instance, using graph databases. So it's another aspect of big data. And the last but not least is value. Usually when we create big data projects or products, when we want to work with big data, we need to achieve some kind of final goal. For instance, it can be any field, basically like financial field, traveling and so on. We want to get some sense out of this data to kind of enrich our data. We don't want to work with duplicates or senseless data because it doesn't bring any value to us. So big data, as I said, has multiple formats, and there is this kind of classification of structured formats, which is more like tabular data stored in relational databases. It's easy to work with using SQL or other query languages. There are also semi-structured formats like JSON, XML. They are semi-structured because there is already some kind of schema with text, for instance, like in XML, but we still don't have the structure of columns and rows as we have in tabular format. And there is also unstructured format, which is text or images. And it's unstructured because we basically don't have guidance in terms of schema, in terms of format of this data. We just have to extract some like common sense out of text, for instance. So we just want to work on the whole text. It doesn't matter the structure. So usually it's harder to process the data which is of unstructured format while in comparison to structured format. So there are multiple spheres where big data can be used. For instance, one of the spheres is traveling. And we can imagine a website where we kind of aggregate multiple routes, multiple flights, and we can choose our destination. And why it should use big data? Basically because we have tons of data about completely different concepts like flights, their prices. We want to set up probably user profiles. So a lot of that, and maybe even build some kind of recommendations. So it can be all powered with the help of big data. Another case where it can be used is smart home. So imagine that we have sensors which measure humidity, temperature, and other values. And with the help of the data from these sensors, we can analyze it and we can build some kind of detection of anomalies, for instance, to track if there was some unauthorized movements, whether temperature is in normal boundaries, and so on and so on. So it's also the case for big data because we can use real-time data processing. We can use some analytics on top of big data and basically use it for machine learning as well. Another very common case is financial sphere. And it's common because a lot of reporting relies on huge volumes of data. So when we build kind of yearly reports or monthly, quarterly reports, we need large volumes of data. It's not that much about precise real-time processing. Instead, it's about like batch kind of processing. So it's definitely the case for big data. And another case is e-commerce. So again, we want to set up user profiles on the website. We want to set up all the information about our items. Maybe we even want to set up some part of the website in real time, build recommendations for users. So it's also the case for big data. So in order to start explaining the difference between big data and data science, I would start with big data as big data engineering field. And I'm kind of biased here because I'm big data developer. But also, I think that data science field is very popular and known to many people, while big data engineering field is not that familiar yet. So I think that starting out with the concepts of kind of tasks that we perform as big data engineers would be valuable in order to kind of build this difference later. So this is how tech stack of big data engineer looks like. Obviously, we don't use all of those frameworks daily in our work or databases. Instead, there are like multiple equivalents. For instance, the various programming languages, various query engines, various databases, and so on. So usually we don't use like all of that in our projects, but it's good to understand the differences and how any of those frameworks work, at least on general level. So one of the important tasks, and probably one of the most important tasks of big data engineers, is building data pipelines. And those can be various types of pipelines, and probably one of the most popular ones is ETL, extract, transform, load. And it means that we want to extract the data from source, transform it in some way, and then write it to some sink or some storage. And for that, we can use, obviously, a programming language. So big data market is mostly divided between Python and Scala. There is still a bit of Java. And there are multiple frameworks which kind of cover all of those languages. And it can be Spark, Kafka, Flink, Apache Storm, Akka, Apache Beam, and so on. And they may work with both streaming data and batch data, or only with streaming data, only with batch data. So we can choose any of those frameworks which kind of maps to our specific requirement. As soon as we read the data from source, process it, transformed it, we want to write it down to the database or storage system. With database, it's quite clear. It can be a relational, non-relational database. It can be provisioned on the premises. It can be provisioned with cloud services. While there is another case as well in big data, which is storage systems, where we can store multiple files in various formats. And such storage system can be Hadoop distributed file system or some cloud service like Amazon S3. And we can also add up a query engine on top of the storage system, which can be Apache Pig, Presto, Cloudera, Impala, and Hive. And those query engines allow to query our data files in SQL nature, which is valuable for users of this data. For instance, people analyzing the data, they can just query it. Or as well, it can be some kind of cloud service for querying the data. Another task is data storage. So big data engineers should work a lot on kind of defining the schema of data, defining how it's located, if it's in terms of file setup, in order to get this data in the most efficient way. And for data storage, databases which are relational can be used, or non-SQL databases. And that's a huge variety of those, as well as some cloud services and databases just kind of on premises or on these cloud storage services. And another task is data processing. And actually, data processing can be an independent task. It can be a part of data pipeline, obviously, as I said before, but it can be an independent task for just getting out the data, maybe some kind of testing, maybe pre-processing for future use, for instance, for machine learning models. So it can be a separate task, a separate step. And for that, as I said, we can use a programming language and frameworks in ecosystem of this programming language. Another task, which is probably not that much mentioned of, is infrastructure. And big data engineers should sometimes set up and deploy frameworks on cloud services or on premises with the help of Kubernetes, Docker, Ansible, or Amazon, Azure, Google Cloud. They can also set up testing a local environment with the help of Python scripts, Bash scripts, and also they may work on defining the metrics and alerting system with the help of Prometheus and Grafana. Also, not all big data engineers work on deploying their applications, but most of the time they need to understand how resources of the system used, which is also infrastructure part. They need to understand how they can use existing resources in the most efficient way and how they can optimize their pipelines. So getting back to the question between the difference of the big data and data science. So many people consider big data as data and data science working on this data, which is partially true. But if we consider big data as a separate field with big data engineers working in this field and data science as a separate field with data scientists working in this field, we will understand that they are different, but they are kind of adjacent to one another. So we will review kind of responsibilities of data scientists and big data engineers, and we'll see how they map to one another. So data scientists may work on data preprocessing. So it's usually features engineering, cleaning up the data to understand whether a schema is like mapping to their expectations, whether they need to update something to build machine learning models. They also work on analyzing the data, understand how it works, how it looks like, and they may also, and of course, they are building machine learning models, maybe even deploying it, or someone else from the team may deploy machine learning models. It can be big data engineers as well. So they are like more concentrated on this side of machine learning and preparation for that. While big data engineers may build pipelines, they may process the data and clean it up and store the data, but usually they may be kind of an independent part of the project, whether it's like completely big data engineering project, or they may serve like a part of the machine learning pipeline. So they may build these ETL pipelines, which will be further used by machine learning engineers or data scientists, or they can help with data preprocessing. But usually it's done by data scientists just because they understand the kind of expected result they need much better. And big data engineers don't necessarily have these skills and knowledge of machine learning. Also, they differ in terms of background, and obviously they can have a similar background because I consider that it's possible to switch to data science background from software engineering and data analysis. But I would tell more in the context of expected skills that they used in order to perform these tasks, which I mentioned. So data engineers usually map the skills of software engineering, math, stats, and algorithms, while data analysts would map data communication and math, and data scientists, they kind of combine it all. I would say that in reality, there is like incline to software engineering on the data engineer side, because big data engineers usually kind of software engineers with the knowledge of big data infrastructure and big data tools. Therefore, they should know much better software engineering. While data scientists should know more about math, statistics, know more about machine learning specific algorithms, and not that much about software engineering, because sometimes it's better for them to conceptually build machine learning algorithms than to think how to deploy those models, because it's not necessarily the kind of task they should perform. And there are data analysts, which usually work more on data communication and building visualizations, like analyzing the data and so on. So we can imagine the background of software engineer and how it can be mapped to both big data and data science. So we can have a JVM stack, which is on the left. So it can be Scala or Java. It can be a framework for working with parsing data like Play. It can be a framework with even working with streaming data like Akka and some connector to databases like Scala JDBC. Or it can be a Python framework, which would be more preferable for data scientists than Scala framework, than Scala like infrastructure and ecosystem or Java ecosystem. And Python ecosystem may have like Django, Flask, and some connectors to databases and knowledge of relational and non-relational databases. And I mentioned here MongoDB because it just happens so that it's probably one of the most popular NoSQL databases outside of big data world. So big data engineers would with having all of these skills, it would be very helpful for them because they would already know how to work with databases, how to parse the data, which is necessary sometimes, how to work with even streaming data in some cases, as well as Python stack, the same like knowledge of working with databases, with transforming the data in various ways. For data science, it would be good for probably deploying models as well as working with databases in general, which is obviously necessary, and with transforming data for pre-processing. Another type of background is data analysis. I call it that way, but it doesn't necessarily mean like analytics as a position. It may mean that there is more like math inclined to background. And it can have like R and Python as programming languages, various query engines like Google BigQuery, Impala, Hive, some tools for visualizing the data like SAS, Excel, Tableau. And this background may allow them in data science to understand how to actually query the data, how to understand its structure, which is a data communication skill that they need. If they are strong in their programming in Python or R, they may be able to like better process the data, which would be helpful for big data engineering as well. But it's more like inclined to math and data communication. Therefore, this background is great for data scientists. So talking about general machine learning workflow, it's like very abstract presentation because there are many steps. There are, for instance, some input data, there is the features engineering, data preprocessing, machine learning models, building them, training, evaluating of those models, and after that, understanding whether we need to do one more time, whether we need to iterate one more time. So in terms of big data, it looks a bit like this. We have a data flow, something happens, it gets into the database, then we read this data, build machine learning model, gather metrics, like in terms of reports, for instance, and here is it. So on the left side, there is a big data side, which is getting some sense out of this data flow, structuring it, building schemas in database, setting up a pipeline to actually move this data to the database. And on the right, there is a data science flow where the data is just taken from the database, maybe pre-processed in some way. Machine learning model is designed and built, and then metrics are gathered from this model. So now I'm going to talk a bit about various practical cases that can be used to understand how data science and big data are operating together. And I will give examples of various frameworks that can be used in each of those cases, which is kind of going to be a bit abstract representation because there may be like many more frameworks or completely different choice of frameworks, obviously. So it's not a detailed representation, but it's kind of a view of how the system may look like, what kind of frameworks may be used, which is helpful to understand how things work and how kind of data engineers and data scientists work together. So first case is about building a data lake. For instance, we have data which is stored in database, and it's kind of comfortable for people to use one database, but sometimes users of this database are getting confused, like whose area of responsibility is that? For someone, it's not that useful to constantly read and write to the database, and they want to have kind of a serving layer which would help multiple users to use this data, which would be a data lake. So like a general representation of this workflow may look like this. We have initial database, and we want, with the help of various ETL pipelines, move this database to data lake. By moving, I mean that we can still leave part of the data in the database, but also another part of the data may move to some storage system, as I described before, like cloud service or whatever else. Or another systems which would allow also querying. And when I'm going to show the frameworks, we'll see which users it can serve as a result. So going from left to right, we have an entry point of PostgreSQL. We store all the data there. Users just go to this database every time they need something. And here's how this ETL pipeline may look like. We can just read the data from this database into Kafka, which is going to be this reliable data queue, storing the data for some time with a retention period. Then we'll have Apache Spark. It's going to be a batch data processing. We don't need here any real-time processing. Our data is already stored in the database. And then we will write out the files to Hadoop HDFS file system. And then we can build up Impala as a query engine on top of this storage system, or we can build a separate storage system, which is going to be like behind this Impala. And we will build one more ETL to move files from one HDFS to another HDFS, which would be Impala HDFS as an example. And also the data can be taken out of Impala using Tableau, which is easily connected to Impala. So here we can have three types of users. We can have users like software engineers who would query either database with some part of the data, or they can use files stored on HDFS. They can just read from there and parse what's needed for them. Another type of users is analytics or data scientists. They can use either PostgreSQL, like part of data there, or Cloudera Impala in order to query some part of data which is stored on HDFS. And for them, it would be a similar experience because it's still SQL. And there is a type of number 3. Which is business users. And by business users, I mean that it's better for them to see graphs or visualizations instead of looking at the data directly. So they can use Tableau with some visualizations on top of this data. Also, there is another case. So imagine that we have a credit scoring system that we want to build. And we have some financial data of these users, like credit cards, some credit history, and we want to understand whether we want to give a credit for this person, like a loan, and we want to kind of get this score, whether it can be on the scale of low, medium, high, or it can be like just like 0, 1, whether we give the loan to this person or not. So the structure may look like this. We can have a data lake or a database even, and store our data there. And from that, we can build our pipeline with data processing, research engineering, and building machine learning model on top of that. It can be a regression, for instance, just a simple model, or we can work with time series data. And as a result, we get a credit score. As I said, it can be of multiple representations. This credit score would be this ultimate goal of this pipeline, and further it can be used, for instance, for web visualizations as well. So here we have two kind of parallel pipelines. So starting from the one on top, we have part of the data in PostgreSQL, which is a historical data. And we can, it's kind of a data of user's history. We want to check out first if we have this user in the database before, because if we did, probably we already have some knowledge about this person, whether he or she is eligible for the loan or not. And after that, we can just connect to the database with some package like CycloPG. This pipeline is going to be fully Pythonic. And then we can use pandas as a library just to read this data using CycloPG. And another part of the pipeline is on the lower side of this image. And it's going to be newer data. So we get the data from our clients, for instance, with CSV files stored on Amazon S3. And pandas can easily read CSV files from Amazon. So another part would be to read out this data, transform it, and then build features. And the part of the data science here and data engineering, they kind of clashing on the pandas, because data scientists may start also doing their processing and features engineering on pandas as well, while data engineers may use it for, again, reading the data from various sources, database or data storage system. And after that, a machine learning model using TensorFlow can be built, and it can be deployed using Flask. So here's again the machine learning and data science side starts from pandas and goes to TensorFlow and Flask. We will consider here that data scientists also deploy machine learning models, but it's not necessarily true. And the result as a credit score will be written to PostgreSQL because Flask allows to do that, so just write to database. And after that, we can have any pipeline we want in terms of displaying it on the website by going to the database, or just checking through our records and making some specific decision on in terms of defining whether we want to give a loan to client or not. Another case that we can consider is, again, the smart home case, which I mentioned before. And we have various sensors, like the ones that measure temperature, the ones that track some movements, humidity, and so on. And this is going to be streaming data, but we also would work with some historical data, which would be needed in this case as well. And we want to build an anomalies detection system. So in terms of structure, it may look like this. We can have a streaming data as the one which arrives in real time, and the batch data as some historical data storage, which can be saved to database or a storage system. And then machine learning model would be built on top of the merge of this batch and streaming data. In this case, batch data kind of represents historical data as well, because we may consider the ranges of our values in terms of their historical ranges. Also, having a history in this case would help to analyze further whether some anomalies that occur are normal or abnormal, like kind of understand their reasons. So still having historical data here is helping. And the result would be detected anomalies. It can be just a range of abnormal values, for instance. It can be some reporting and analysis on top of that as well. So it can look like this. Starting from the top pipeline, we can have, it's a batch data processing. We can have files of our data type on Amazon S3 as a storage system. And Apache Spark works very well with that kind of format. So Spark will just read this format, transform it in any required way, and write out the results of PostgreSQL. That's all for batch pipeline here. A streaming pipeline would connect to some kind of API, doesn't matter which one in this case. It can be specific to the sensors. And then we will use Play framework for connecting to this API, reading the data, and then using Spark streaming framework in order to read the data in real time. The machine learning part here starts from the usage of Prophet framework, which is made by Facebook. And this framework allows to work with time series data. In this case, we have sensors values, which are time series data. And this framework would be able to read batch data from PostgreSQL database by just connecting to it, and as well as connecting to Spark streaming and reading the data from it. And then This machine learning model built with Prophet can be deployed using Flask. And as we know, Flask can write results to PostgreSQL. After that, the results can be used for some visualizations in Tableau or just for using it for other applications which build analysis on top of the anomalies detected definition. So here we have like more strict the diversion of data engineering and data science responsibilities, because we can see here that data scientists would start their work on preprocessing or working directly with Spark streaming data if data engineers would preprocess it in the necessary way, or just working with the data which is stored in the database, which is again mostly structured in this case. Here I just kind of missed this step of possible preprocessing, which can be done by pandas, for example. And that may happen as well because machine learning models are not built from just the data flowing into the system. There's still some kind of preprocessing required. But still, we can see that even though this pipeline may look a bit complex, most part of the work of data engineers to practically move the data to machine learning models. And case number 4, imagining a recommendation system. It can be a recommendation system of movies, songs, or anything else. So in this case, for instance, we will choose movies, and users on the website would have some information about them, which would help to kind of map what they like. For instance, their ratings of the items that they liked before, also their new ratings. And that would be helpful to understand what we want to recommend for them and what would be suitable. So in this recommendation system, we have user and item ratings. We have a data lake or database where all of those user and item ratings are stored, or any other additional data. And we want to build a machine learning model using this data lake, and the result would be recommendations. So the pipeline may look like this. We can have data in JSON format. Let's imagine that that's the way we store our data from the website, or we parse it somehow. And we can use for streaming data processing here Apache Flink. Let's consider that we want to process the data in real time. The result of processing would be files in CSV format. Then in CSV format, we can read those files using pandas, transform them, engineer some features, and then a library called Surprise for building recommender systems would work well with pandas transform data. And it can be deployed with Flask again. The result would be written just to PostgreSQL. So here's the part of work which is basically before pandas is big data engineering work, where we just transform the data from one format to another. Maybe some part of working with pandas, but mostly it will be data science side. And here we can see that the bigger part of pipeline basically is data scientist work because of the specificity of this case. Mostly like an example of these frameworks, but obviously there can be a different setup. So as we can see here, there are multiple differences between big data engineers and data scientists, and big data and data engineer and data science in general. And they fall on different categories. First of all is goals. And they obviously want to both achieve some kind of general goal to gain some business value, for example, but they are different in terms of kind of implementation of these goals. So big data engineers mostly have technical goals, like maintaining reliable pipelines, maintaining reliable systems, defining a proper structure of the data, while data scientists would have more business-oriented goals, like helping to increase revenue with the help of building machine learning models. So that's the first difference. The second one would be responsibilities, and that's what we consider. that data scientists have more responsibilities around building machine learning models, while data engineers concentrate more on building data pipelines. Another difference is background, and it's more about needed background for specific profession or kind of position in this case. And in terms of background, a data scientist would fall more to the side of math and statistics, while data engineers would be more on the side of software engineering. Another difference is results of work. I would say that data scientists have more visible impact because they rely more on performing business tasks, and some of their machine learning models may have a direct impact on this task, like again, increasing revenue, for example. While big data engineers have more kind of invisible results of work, but they help to maintain this system to create it in the first place. So here's my contact info, like my Twitter, GitHub, LinkedIn, and you can find out some of the previous talks I did on my speaker deck. And thank you for your attention.
Thank you very much, Roksolana. Very, very great presentation. We're just gonna wait a few moments to see if we have immediate questions here in the chat. In the meantime, I guess I would like to inform everyone that you can go to the chat allocated area where you can directly ask questions Roksolana herself. There's about 9 people able to join the room with the video, and many more can listen in. Right, so no questions popped in the chat, so I guess this is it, Roksolana, here for our live stream with you, and I invite you to join the allocated area for Q&A there. Thank you very much, and see ya.